I'm Dr. James Millen. I'm Reader in Advanced Photonics at King's College London, and I run the levitated nanophysics group, where we study how physics changes at the nanoscale and how we can exploit those changes. I'm also the director of King's Quantum, our institutional research centre, which is a multidisciplinary research centre with the aim of exploiting quantum technologies in the real world. And I'm also lecturer in quantum theory to the public at the Royal Institution of Great Britain. We're going to take a cutting-edge, very new emerging imaging technology called neuromorphic imaging and apply it to an equally cutting-edge sensing technology using levitated sensors to build a whole new sensing platform. Our research will involve the development of new tracking algorithms, bespoke hardware, and the coding of microprocessors to really produce a commercially viable sensor that's very, very robust and able to be deployed in real-world settings. You can build an incredibly delicate sensor that's incredibly high precision. For example, if you want to do some fundamental physics experiment where you're trying to detect dark matter, then it doesn't matter if your sensor is so delicate that you have to bury it in a precision research lab in the middle of a mountain or something, because it's only designed to detect tiny, tiny forces. But if we want to put a sensor, for example, inside our phone, it's got to be able to withstand being dropped, being knocked around, and it's still got to function, and it's got to not be destroyed. So that's what I mean by robust. I mean a sensor which we can really use in everyday life. The really exciting thing about levitated sensors is that they have the potential to operate in the quantum regime. So this means that we could operate this sensor as a quantum sensor, which has a lot of implications, but really just means the sensor gets even more sensitive and you can start detecting such phenomenally tiny forces that honestly, I think the scientific community hasn't even come up with all of the ideas as to what we'd do if we had this technology. But a very obvious starting point that people think about is in navigation. If you have incredibly precise sensors, then, for example, you can navigate an autonomous vehicle around without having to connect to GPS. And so if you went into a tunnel or there's a GPS outage, then it wouldn't affect your navigation anymore. But that's just one example of why a quantum sensor would be important. I think there are three major areas of application I would like to focus on. The first one is the detection of gas and tiny little flows of gas. This may not sound very interesting, but actually understanding the flow of gas out of the surface of materials is a huge industrial problem and one of the main hindrances in a lot of space technology, because once you get a device up into space, gas comes out of the surface of the material and can completely change the behavior of your satellite, for example. And this is a process that's very poorly understood and hard to monitor on the Earth. And levitated sensors can be moved very, very close to a surface, and they're sensitive, so you can detect even tiny flows of gas. Detecting gas also has a more industrial application as well. So if you're developing very, very high technology materials with very, very sensitive surfaces, for example, optical coatings in photovoltaics, tiny, tiny changes in the flow of gas near that surface can change how these devices behave when you apply them. And if you're in some huge industrial process, like the creation of photovoltaics, even a tiny optimization in that process can lead to huge changes in the energy efficiency of the process, but also in the cost of making these materials. The second application, which I've mentioned a bit already, is in navigation. So if you levitate your sensor and your entire device moves, the sensor is sensitive to that. And this allows you to detect the rotation and the motion of, for example, a car within which the sensor is. This is a massive field of study, especially in autonomous vehicles, because it's amazing how hard it is to know where a car is without tracking it using GPS. And GPS is not always reliable. You might be under the sea if you're a submarine, or you might be in a tunnel if you're a car, or GPS might just go out. Or maybe you don't want to keep putting satellites up into Earth orbit. So navigation is another huge area of opportunity. And the third area is quantum sensing, like I said. Quantum sensors are predicted to be so sensitive that actually I think researchers haven't caught up with understanding what they can use them for. But one example I'd like to give you is I've talked about the flow of gas. Well, if you have a quantum sensor, you can actually detect the flow of light. You can detect individual quanta of light, which are called photons, if you have a sensitive enough detector. And this, if you put it near a surface, will allow you to detect the temperature of that, because temperature, heat, is actually just the flow of long wavelength light. So you could use this for very, very precise, spatially resolved thermometry near surfaces. But also, most biological systems also emit light in their operation. You can move these sensors into biological settings and monitor incredibly tiny little bioprocesses, for example, photosynthesis, if you have quantum enhanced sensors for light. Precision sensing can be used in environmental science in a whole range of ways. I've talked about how levitated sensors could optimize industrial processes, and making these huge scale processes, I don't know, the construction of semiconductors, even 1% more efficient leads to massive energy saving and also material saving. I talked about navigation, and if, as people imagine, one day all vehicles are autonomous, then optimizing their motion will also be a great fuel and energy saving as well. There's also a real hope that quantum technologies can contribute to climate science, particularly in the realm of Earth monitoring. So if you have incredibly sensitive sensors, you can start to detect small changes in the Earth, for example, small amounts of erosion or movement of matter underground. And this helps us understand the shifting Earth and the climate better, and improves our models for predicting how we can improve environmental science in the future. And quantum sensors exist. You can go out and buy them. A couple of really good examples include quantum magnetometers, which can detect the tiny magnetic fields from your brain in a much less invasive way than MRI, and quantum sensors of gravity that can detect tiny changes underground, such as the flow of water in an underground river, and it's used for surveying. And both of these examples rely on tiny atoms and electrons. And if you extend your quantum sensors up to nano and microparticles, like we use in my research, then the sensitivity of your detectors starts to get mind-boggling. In a way, I think we haven't fully grasped the implication of this.